Welcome to the Crazy Hat Chemist. So another video here on equilibrium. So let's get moving. Bam! So this is a generic equilibrium practice. Okay, and by doing this problem, you should be able to do any equilibrium problem. This is generic in that there are no real formulas, no real elements here on this. But it will give you the foundation in how to do any other equilibrium problem in terms of shift changes, either shifting towards the reactants or shifting towards the products. Okay, so let's read out what this fictitious equation is. So it's 2 moles of X2 in the gaseous state plus 4 moles of Y in the aqueous state plus 5 moles of Z in the solid state. Those are the 3 reactants. I got those double-headed arrows there to let me know that this is an equilibrium reaction and not a unidirectional reaction. That means that this reaction will go either towards the products or towards the reactants. I can approach it either both ways. Then on the product side, I have 2 moles of A in the liquid state. I have 3 moles of B in the aqueous state. The other thing I have here is the delta H, that is the change in enthalpy, is equal to 5 kilojoules. Okay, so let's figure out what the questions are, and then let's proceed step by step in answering those questions with the information that we know about equilibrium reactions. All right, so let's get moving. So our first question is, what is the KEQ? The KEQ is the equilibrium constant expression, and that is products over reactants with the stoichiometric coefficients as exponents. I'll repeat that. The KEQ, the equilibrium constant expression, is the products over the reactants with the stoichiometric coefficients as exponents. Now, the question is, what is not included in K expressions of any kind? So what states of matter? Solids and liquids are not included in K expressions. Gases and aqueous most certainly are included. So what I want you to do is write out the K expression right now, and then it will pop on the screen here in just a moment. Excluding the solids and liquids, with these products over reactants and the stoichiometric coefficients as exponents, this is what you should get. KEQ is equal to, in the numerator, I got B to the 3rd power, these are brackets, and then X2 to the squared, that's to the 2nd power, and then Y to the 4th power. All right, so that's what you should get. You should see that you did not include the A because that's a liquid, and you did not include the Z because that is a solid. All right, so what does this mean? And I actually alluded to what the delta H means already before, and that is the change in enthalpy. The enthalpy is a heat term for the reaction. But knowing that this value is positive lets us know which side of the reaction it goes on and the type of reaction. Okay, so which side of the reaction will it go on knowing that the value is positive? It doesn't matter if it's 5 kilojoules, 0.5 kilojoules, or 500 kilojoules. The numeric value itself doesn't matter at this point in time. Okay, what does matter is the sign. Since it's positive, it's going to go on the reactant side. Okay, and then you can actually answer this question knowing the sign of the change in enthalpy. Is this reaction endothermic or exothermic? Okay, endothermic is heat requiring, exothermic is heat liberating. So since this enthalpy change is positive, we know that this is endothermic. If the value were negative, then it would be belonging on the product side and it would be exothermic. Okay, hopefully you got that. So what is the shift in equilibrium when? So we're going to have a bunch of different things that we're going to either add or subtract, and we're going to figure out which way the equilibrium will shift, to the right, to the left, towards products or towards reactants. That's what we're trying to do. And remember the lecture on up, up, and away, and downtrodden. Okay, that is what I'm focusing on right now. Okay, if you increase X2, which way will the reaction shift? So I'm going to increase the X2, and then I am going to go up, up, and away. So I'm shifting away from it. Now, you might think that this is going towards products, of which it is, but when you shift towards the products, you decrease the amount of X2. Remember, this is a balancing act based on Le Chatelier's principle. Okay, so it's going to be a shift to the right. What would occur if you decrease Y? So there's Y on the reactant side. I'm going to decrease the Y, and it will shift towards it to make more of it, okay, since it's on the reactant side. So So that's a left shift towards reactants. Okay. All right. The next one is what happens if you increase Z. So if you increase Z, now notice the state of matter of Z. It's a solid, and solids are not included in the K expression. So do they affect the value of the K? Absolutely not. Is it required that Z be part of the reaction? Yes, because you cannot have a reactant missing from the reaction. So it's important that Z is there, but it doesn't really matter how much Z is there so long as Z is there. So there's no change because this is a solid, and that's kind of verified in looking at the K expression, and that Z is not in the K expression. Okay. What happens if you increase B? Now notice B is on the product side. It's aqueous. I'm going to increase the B, and I am going to shift away from it. That's up, up, and away. Okay, and that's a shift towards the reactants, which is a shift to the left. All right, next one is what happens if I decrease B. So if I decrease B, which way will it shift? To the right or to the left, or towards reactants or products? I'm going to shift towards it if I decrease B, and that is a shift to the right towards products. Okay, what happens if I were to add xenon, which is a gas? So xenon is a one of those special gases on the far right hand side, and that is a noble gas. I learned it a long time ago as an inert gas, but they don't react readily with other compounds, and xenon doesn't react with anything that's in here. So since it doesn't react with anything and it's a gas, it's just going to increase the total pressure, and there's going to be no change in the equilibrium, i.e. there's going to be no shift in the equilibrium either towards the right products or towards the left of reactants. Okay? All right. Now, what would happen if I increase the heat or add heat or increase the temperature? Now, remember, this is all dependent on the enthalpy change term, and that is 5 kilojoules. Since it's positive, I know it's endothermic. Since it's positive, it goes on the reactant, so it's reactant side. So my heat term is actually on the reactant side. So if I increase the heat term, it will shift away from it, and that is towards the products, which is towards the right. Okay. All right, what happens if I were to decrease the pressure? Now, in the previous lecture, you need to review the previous lecture dealing with equilibrium shifts, where I talked about 3 different types of reactions and also pressure-volume relationships. So you need to remember what the pressure-volume relationship is, and the pressure-volume relationship is an inverse relationship. That means if the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up. Right now, the pressure is going to decrease. So that means what's going to happen to the volume? The volume is going to go up. And what we're going to do is we're going to follow the volume. That is, we're going to do whatever the volume does, but in terms of moles of gas. This is very specific. You're going to do whatever the volume does. The volume is increasing, so you're going to do whatever the volume does in terms of moles of gas. So it's going to shift towards the side with the greatest number of moles of gas with an increase in volume. If the volume were decreasing, it would shift to the side with the fewest number of moles of gas. So what I want you to do is I want you to look at the reactant side, okay? And I have X2, which is a gas. I have Y, which is aqueous. So I'm going to ignore the Y, which is aqueous. I'm going to ignore the Z, which is a solid. That's on the reactant side. I don't have to worry about the enthalpy term because that's certainly not a gas, that's a heat term. On the product side, I have A, which is a liquid. I'm going to ignore that. I have B, which is aqueous. I'm going to ignore that. So how many moles of gas do I have on the reactant side with the X2? I have 2 moles of gas because the 2 stoichiometric coefficient on the reactant side. How many moles of gas on the product side? 0 moles. So I'm going to shift to the side, since the volume is increasing and the pressure is decreasing, I'm going to shift to the side with the greatest number of moles of gas. The reactant side has the greatest number of moles of gas, so I'm going to shift to the left towards reactants. Okay. All right, now I want you to notice something in regards to these arrows here. I want you to look at the double-headed equilibrium arrow, which is approximately in the middle of this problem, right? It separates the reactants from the products. Now, what I want you to do is I want you to look at B on the right-hand side. If something on the product side increases, it shifts to the left. If something on the product side, for example, B, decreases, it shifts to the right. Okay, so if I were to increase anything on the product side, it's going to shift towards reactants. If I decrease anything on the product side, it will shift towards products. This is assuming that it's not a solid or a liquid, okay, or a non-reactive gas. Now I want you to look at the reactant side and look at the X2 and the Y and look at the arrows here. If you increase anything on the reactant side, you're going to shift towards the right, towards products. That's X2. If you look at Y, if you decrease anything on the reactant side, it will shift towards it, and that is towards reactants. Notice how these arrows are situated with both X2, Y, and B, and in relationship to the double-headed arrows of the equilibrium. Okay, you should also observe this with the heat term in the 5 kilojoules. The 5 kilojoules is increasing like the X2 is increasing, and they're both shifting to the right. Okay, now this is assuming that none of these things that I'm talking about are solids or liquids, because those, just like the Z, doesn't have a shift. It doesn't change. It doesn't shift the equilibrium. Make sure you note that. Those arrows are very important which direction the equilibrium will shift. All right, now we're going to add a catalyst to this reaction. So there's no change when you add a catalyst. It lowers the activation energy barrier. That's the E sub A. Okay, it increases both the forward reaction and the reverse reaction. That means this reaction just happens faster towards products and towards reactants, but it doesn't cause a shift in equilibrium towards the right or towards the left. It doesn't affect the KEQ value, in other words, okay, because there's no shift in the reaction. But it does make the reaction happen faster because that activation energy barrier has decreased, so it makes the reaction occur faster in both directions. Okay. All right. If the value of the KEQ is 3.2 times 10 to the negative 3, is this reaction reactant or product favored? So remember that KEQ, when it's 1, it is at equilibrium. So this number is not at 1. When the number of the KEQ, the value of the KEQ is greater than 1, then it's product favored. When the value of the KEQ is less than 1, it's reactant favored. Since this number here has an exponent that's negative, that means that this value is less than 1 and it is going to be reactant favored. So when the KEQ is less than 1, it is reactant favored. Okay. That means if I were to draw those double-headed arrows again, I would draw a longer arrow towards the reactants, a shorter arrow towards the products. That would indicate that it is reactant favored. Okay, another item here. So this is a lady here balancing, okay? And this whole generic equilibrium practice, as all equilibrium reactions are, they are all based on Le Chatelier's principle. If you put a stress on something, then that system will modify and make a change to reduce that stress, okay? And that's why when you're increasing something like B, you shift it away from it, so you decrease it, okay? When you decrease B, you shift towards it, okay? So it's kind of like this door that goes back and forth, and you're going to either shift to the right or shift to the left. It's like that lady there balancing, okay? And if she moves either her right or left hand, then she's going to have to make a shift in her weight, and she will establish a new set of equilibrium conditions of which she will still be balanced, but it will look differently, okay? Hopefully that makes sense for you. I am the Crazy Hat Chemist, and this is great hat here. So the question is this an element? What is the element? RB, what element is that? Is that rubidium? It is rubidium, but this hat is not for rubidium. This hat is for root beer, and root beer is my favorite soft drink. Not that I drink a lot of root beer, but it is my favorite soft drink. So give me a thumbs up if you like that video. Subscribe to my YouTube channel. Find my website. Online, there's lots of great reinforcing worksheets. I'll see you next time for more cool chemistry problems. Bye for now.